The learning objectives here is define the attributes of a concurrent force system. All that a concurrent force system means is just like it sounds. If it's concurrent, it means the forces intersect. And so we just have to have those lines of action have to intersect somewhere. And then we can do two things with the dot product. And we're going to focus on these two things for statics. We can calculate the angle between two vectors. And then we can also do, and actually this is the one that we're going to be focusing on even more, is finding the magnitude of a vector parallel and perpendicular to another line. And then also express those found magnitudes as Cartesian vectors. So we can find it as a scalar, parallel and perpendicular stuff, or we can find it as a vector. So that's what we're doing today. That's what we're responsible for. That is what we need to be able to do. Our first homework problem here is asking us to use, and this is the one that would be due next Tuesday. And remember, when you start the homework problems, that for the hand, every single problem on mastering is going to show up as a handwritten homework problem. And so I would just, when you look at this homework problem, write down the given information, draw all the given stuff, write down what you're asked to find, and then start writing in your solution here. And remember, in your solution, if you do some stuff and then you realize, oh, you know what, that's not right. And you do some more stuff and you realize, oh, you know what, I should have done that up here first. That's totally fine. What I see a lot of people doing is they'll do it once and then they'll copy it over to E2 paper and make it all nice and pretty. Think about it more as a progression through the semester, where this first couple assignments or even first half of the semester maybe doesn't look so great, but you get better as the semester goes on and you become more efficient. And also, don't be afraid to add notes to yourself over here, like, oh, why did I do this? Or, why did I do that here and not on this other problem? Now, what we're dealing with here on the dot product is asked to find the parallel and perpendicular components. So, like, say this was the A to D right here, and then we have the force vector over here. What we're going to be able to do with the dot product, and this is a three-dimensional vector, or this is a three-dimensional line, and then we have a three-dimensional force vector. What we're going to be able to do with the dot product is find what of this is perpendicular to that line and what of that original force vector is parallel to that line. So that's what we're trying to do with the dot product. We have another one, determine the magnitude acting along the line from A to B from this force vector right here. So we're going to say, well, how much of that force vector is projected down onto that line right there? And then our third one here, find the components parallel and perpendicular to this line from A to B. Notice you have a planar projection. So actually we have to start this problem by just formulating that force vector into X, Y, and Z components before we can even start. So like I said, we're going to start seeing this planar projection stuff is going to occur quite a bit here as we move forward. It's not just like, okay, we're done with that topic, let's move on. We're going to see a lot of that in statics. So really encourage you, if you're not understanding something and you look at the homework and you're just like, okay, I kind of get it, you come into office hours and let's resolve that deficiency, because that's going to build for multiple lectures. And if you resolve it now, then those next lectures are going to be even easier. Okay, so let's talk about the dot product here. And let's write down a few things, and we'll write down some procedures, and then we'll jump into an example. If we have a couple of vectors, let's say we've got a vector here, and I'm just going to call that vector A, and vector A is three-dimensional, so it's an AX in the I plus an AY in the J plus an AZ in the K direction. And then we have another three-dimensional vector, and they're concurrent right here because they intersect. So they are concurrent right there at that spot. And then point B, or vector B, is going to be a BX in the I plus a BY in the J plus a BZ in the K direction. And then I see a question in the chat here. As long as the format and header is correct, is it okay to write the handwritten homework on the computer? Absolutely, yeah. If you have like an iPad, if you're doing it in OneNote, absolutely. You know, I even see people, instead of drawing the given information, they'll take a screenshot or they'll copy the picture from mastering and just put that as their given information. That's totally fine. If it doesn't say not to do it on the rubric, then you can do it. The rubric is really straightforward, really simple, and that is very intentional that we did that like that. Okay, so if we have these two vectors, great question, Sydney. Thank you for that question. We can say a couple of things. We can say that A dotted with B, and so that's a dot product, is equal to the magnitude of A times the magnitude of B. And you're going to see me use the dot for all instances of multiplication. I don't want to put an X because I don't want somebody to think like, oh, is there an X variable in there or something like that. But you'll see me, if a dot, we know it's the dot product when it's vectors. When they're two vectors multiplied together. We know it's not the dot product when it's a vector and a scalar, or if it's two scalars multiplied together. But you're going to see my notation there is the same. And then times the cosine of theta, and that theta is the angle between those two vectors. So wherever those two vectors lie, whatever plane those two vectors lie in, we can find that angle theta from those two. This part of the equation, A dotted with B, that is basically what that's going to give us, that A dotted with B is just the product of the sum of the components. And so that is going to be AX times BX plus AY times BY plus AZ times BZ. And it's going to give us a scalar, right? So this part of the equation over here is going to give us a scalar. And so we have two really important things that we can do with the dot product. So two things for us that we will do with the dot product, two important applications, and those are, number one here is going to be, we can find the angle between the two. And these are in line with our learning objectives. That was one of our learning objectives. So theta would be the inverse cosine. And all I'm doing is just solving this equation up here. So I'm just taking that equation and solving it for down here. Theta would be the inverse cosine. And then wouldn't it be A dot product with B on the top, which is our scalar, divided by the magnitudes A times B. And we can put a note on here, right? These A dot B, those are magnitudes. And so we know it's not the dot product, this is multiplying those two together. And then the A dotted with B, that's actually the scalar that we get right here. And so that's this part, right? That's the numerator in that equation right there. So there's our first one. Actually, you know, that one is pretty straightforward. We're probably not going to see that one that much for us. Number two, though, we're going to see, this is what you saw in pretty much all the homework problems. I think you're asked for the theta once on your homework problems. Number two is to find the parallel and perpendicular components. Yes, concurrent, that's correct. I see a question in the chat. How do you define a concurrent again? It's when two lines meet or intersect. Yes, absolutely. And so let's say we have a line here. And so let me just draw this line. And it's a three-dimensional line right here. And we have a force that's applied to it. And so let's say we have this force here, FA. And that force FA is a three-dimensional, it's a three-dimensional force vector. Well, what we're going to do, and so we can call this point right here, let's call that point A, and we can call just a point down here A, we'll call that line from A to B, okay? Now what we're going to be able to do, the parallel and perpendicular components, what we're talking about, is let's find the perpendicular component. So this would be the component right here that's that's the component of FA that's perpendicular to AB. And then the other component is this one down here. Remember, these are all going to be 3 dimensions. That one is going to be the FA onto AB, or we could call it, that's the parallel component. So I like to, just to like make everything super clear, I call it FA onto AB because it's really the projection of A down onto that line from A to B. Now, the way that we can find this is we're going to go, we can find FA onto AB is, we're going to get a magnitude if we take that original force vector and dot it with a unit vector from A to B. That's going to give us the magnitude of that FA vector projected onto that line from A to B. And we do end up, when we do the dot product, we get a scalar out of it, right? These are 2 vectors. The unit vector, it's a unitless vector. And remember when we first talked about the unit vector, we talked about how it's really a alpha, right? It's the cosine of alpha, it's a cosine of beta, it's a cosine of gamma. And I showed you that video that had that 3-dimensional coordinate system, and it showed you that alpha was a right triangle, or an angle in a right triangle, that beta was a right triangle, and that gamma was an angle in a right triangle. And so if you think about this, what we're really doing, since the dot product is taking the x component of the force, oh, and this should be FA. Let me highlight what I just added there. I just added the A subscript right there. What we're really doing is we're taking the x component of the force and we're multiplying it times the cosine of the angle. And so it's still just a projection, right? Remember the cosine of alphas, those were projections too. And so we take the x component of the force vector, multiply it times the x component of the unit vector. That tells us how much of that force vector is projected along the x part of that line from A to B, and then the y part, and so on. So we can always use this equation to do this. And actually, so it's really pretty straightforward, right? It's just F dotted with a unit vector. The force vector dotted with a unit vector will always give us the parallel component right there. And then if we want to find the force vector, so now FA onto AB. So we, out of the dot product, we get a scalar. So we have, this is the dot product, and we end up with a scalar there. Now, if I have now, so, you know, if I have this line from A to B, and I have this force vector from FA, and, you know, maybe it's 200 pounds. And then I found, oh, you know what, there's 75 pounds that's going parallel to that line from A to B. How can I take that 75 pounds and convert it back into a vector? Right, we started with a force vector, we converted it into a scalar. What do I need to do with that 75 pounds? What do I need to do with that, you know, this magnitude, FA onto AB, to get it into a vector? Anybody have any ideas? We used the equation last time. It was like one of our main equations. If we have a magnitude of something, what do we multiply it by to get it into back into a vector? And actually, let me ask, let me see, N through I is last name here, Maxwell, and walk a uku. I'm not even going to try. You can pronounce it for us though.
Yeah, it's Wokuku.
Wokuku.
Yeah.
Any ideas, Maxwell?
Would it be the unit vector?
Absolutely. Yes, it's the unit vector along that same line from A to B, because we know the magnitude and we just have to multiply it by the unit vector, and right, and then that'll convert that back into an actual force vector. So there we go. Absolutely. Okay, so that's to find all the parallel stuff right there. So this was, and let's put a box around this right there. That's to find, this is giving us the parallel. And so we have both the the scalar, right? So if they ask us, some problems you're going to see, they ask us to find the magnitude. And so we would just do the first equation. Some problems are going to ask us to find the vector. So we have to do the first equation and the second equation in that case right there. Now, that takes care of really the majority of the work for us. But when we do want to find the perpendicular components, the idea of finding the perpendicular components is that the components, the idea here, and let's put this as the idea, is that the components have to add back to the original vector that we started with. So if I think about this in terms of a scalar approach, so the scalar, that means that we have our original vector, FA, and if we're breaking something up into components, the parallel and the perpendicular, well, we actually make a right triangle. So FA squared is going to have to be equal to FA onto AB, and these are all magnitudes squared, plus FA perpendicular to AB squared. And then we can just solve this. So we can say, well, FA perpendicular to AB is going to be the square root of FA squared minus FA onto AB squared. So it's just the Pythagorean theorem, because we have basically the parallel component, the perpendicular component, those are at 90 degrees to each other, so we have a right triangle, so we can always just do the Pythagorean theorem. For the vector stuff, if we're wanting to do this in terms of a vector, it's the same thing, but when we've already got it written out as vectors, so our original vector, FA, has to be equal to the FA onto AB vector plus the perpendicular, the FA perpendicular to AB. And so we could just rearrange this one, and we can find FA perpendicular to AB as FA vector minus the FA onto AB. And so we always have to start over here. So we always start with these, because no matter what they're asking us for, we always have to find the parallel component using the dot product. So we always start with the dot product in this case. And I see some stuff going on in the chat here. Multiply by cosine of theta. I think that was a little while ago, right? Yeah, multiply by the unit vector. Okay, excellent. So I think that was with regards to my question from before. So always got to start with the dot product. And then you can see, once we get that dot product, right? Once we do that right there, well, we can, if we want to find the parallel vector, then we can go to this equation. If we want to find the perpendicular component, well, then we can go to this equation. If we want to find the perpendicular vector, then we can go to this equation. But they all have those first two equations that we wrote down that we boxed in red over there. Any questions about any of this? Should be pretty straightforward, right? I mean, nothing like super crazy mathematically or anything like that, but it is important that we understand conceptually what's going on. And I also know that these equations can be like, they can look totally new, right? Like, this is the first time you maybe are seeing them written like this. Maybe you've seen them in math before, but really think about what's going on here. Maybe you know, you need to add some stuff to this and say, just to remind yourself, okay, you know, this is the perpendicular, you know, as you're going through the homework, again, taking those notes off to the side there can be super valuable. Okay, so let's do an example now. And we're going to actually extend one of our examples from last time, the one, this one that I had up on the board over there, where I had that tape up there. And this is the one that we did for the position vectors. And so last time, let's draw our 3D coordinate system here. And so we had the x-axis going off to the right. We have the y-axis going up. And then we have the z-axis coming out of the page here. And then we had our orange strap. And this orange strap went from A to point B right here. And we had said that, oh, you know what, point A, and leave some room back here. We had said that point A was at 0, 0, 0, and then point B up here, we said that was at 2, 3, and 4 feet. And we had actually gone through in the last class, and we had found that the force vector from A to B, and we did it with the position vector into the unit vector, and we had found that it was 74I plus a 112J and plus a 148 K hat. And that was going to be in pounds. Because, and we started with the fact that we had a magnitude here equal to 200 pounds. So that magnitude of 200 pounds, we found this from last class. We did this part of that. So we said, okay, well, what's the force vector from A to B? Well, remember last time, you know, when we were doing this, if I really put 200 pounds on there, if I really put 200 pounds on that tape right there, you know, I end up tearing the tape off of the board there. So what I did is I brought in I brought in a stake here. It's actually from civil engineering field session. We use these in civil engineering field session. So I brought in this stake, and so what I figured I would do is I need a hammer. I think I forgot my hammer, but I was going to hammer this into the wall here, and my wife and kids would be like, "What the heck are you doing?" So I'll hammer this into the wall, right? And then we can attach this to there, and hopefully it'll actually hold the 200 pounds along this stake here. And so we could also think about this in terms of where this is going to fall in our coordinate system. So here's our coordinate system, right? We have the X, Y, and the Z right there. I'm going to pound this stake in like this, right? So I'm going to try to get that stake going back into the negative Z direction, and then hopefully that'll hold the 200 pounds that's on that strap. And so hopefully this doesn't come like shooting out of the board at me. But what we're going to use the dot product for is we're going to try to figure out, okay, if I have this wooden stake that's right here, then I want to know, you know, how much of that 200 pounds is actually going along that wooden stake. So I want to find the parallel components, and I want to find the perpendicular components, so that I know, like, okay, you know, maybe it can hold 100 pounds, and, you know, or it can hold 115 pounds or something like that. And I say, well, how much force is actually acting on that thing right there? Let's, for the sake of this example, I'm going to call this point C right here. And that point C has coordinates, and to make this a little bit more like the homework, has coordinates of negative 0.2 in the X. It has a coordinate of 0.3 in the Y, and it has a coordinate of negative 0.93 in the Z. So just like we were given the coordinates of A and B, let's assume we're given the coordinates of C right there. And actually this stake is exactly 1 foot long. If you put it on here, oh, I guess it's like barely shy of the 12 inches right there. So, but we'll just assume it's exactly 1 foot there. And so what we want to find for this problem then is, let's find the components of FAB. We want to find F. Well, let me write this. The components of AB of FAB that are parallel and perpendicular to AC. And we want to do this for two parts. We want to do part A. We want to do the scalar stuff. So this means magnitudes. And then for part B, let's do the vectors. Then we can find the vectors that are parallel and the vectors that are perpendicular. All right, so we've got our problem set up here. And so let's jump into the solution. Let's figure out, because I mean, that stake really, like where I'm sitting, and it would like come out of the board and probably like hit me in the head and you know, like, and knock me out. And then, you know, I've actually thought about this, like, what if something happened to me and I was down here in my basement and like all of a sudden, like you guys see me like pass out or something like that. And like, you have no idea, like, who would you call? Like, you don't know where I live or anything, right? Like, hopefully my wife would come down and check on me in like a couple hours or something like that. Or I don't know. I thought about that. I don't think, you know, I don't know. I think maybe my wife would notice that like I wasn't making any noise down here or something, or my kids would come down, or maybe the dogs would start barking, or my cat would start meowing, or my chickens would start like clucking away or something. So okay, so we don't want that thing to hit me in the head, right? So let's figure out how much force is acting along that wooden stake. And so think about this, right? In terms of our real system, so here's the x, y, and z. Our force vector is like here. Our force vector A to B, that's 74. And then the stake that was sitting back here like this. And so we want to figure out, you know, how much of that stake, or how much force is acting on that stake there. So for part A, this is the scalar part here. How can we find, we want to find FAB onto AC. And so what do I need to write right there? Remember, we're always going to, let me start this. We're always going to start with the dot product, right? It's got to be the dot product here. Mackenzie Jones, what should I have on the left side of that dot?
Sorry, I'm looking.
So is it going to be, what kind of vector do you think it'll be?
It would be the the vector A, not the vector A, the component for A.
It would be the force vector, right? Mm-hmm. It would be so it would be the force vector from A to B. And actually, you know, I said the left side, but is the dot product, does it matter what order I put the vectors in for the dot product? No, it actually doesn't, right? But we wrote it originally on the left side. And then, Mackenzie, while I've got you on here, how about the right side?
That would be the unit vector.
Oh, wait, and it's not, oh, the unit vector, okay, yes. FAB, so that's correct. And then the unit vector from where to where. And actually, you got the unit vector, so let me ask somebody else here. How about Ted Kim? What unit vector should I use? I saw.
Let me see real quick. The one along AB, right?
Not the one along AB. Which one are we trying to project onto?
Oh, AC.
AC, absolutely, right? Okay, and also notice that these two are concurrent, aren't they? Right? I do have this intersection point here. Let's add a note to that right here. So we can say that FAB and the unit vector from A to C are concurrent because they intersect right there. Okay, yeah, so we have the FAB dotted with the unit vector from A to C. We are going to need the unit vector from A to C here. We were given the force vector from A to B, right? But the unit vector from A to C we would find as the position vector from A to C divided by the magnitude of the position vector from A to C. And so we're going to end up, let's see, a minus 0.2, a 0.3, and a minus 0.93 would be the position vector to get from A to C. And remember, we can always mathematically, we can always say it's final minus initial. So it'd be a minus 0.2 minus 0, a 0.3 minus 0, minus 0.93 minus 0. And then the magnitude would be 0.2 squared plus a 0.3 squared plus a 0.93 squared. Now, I told you all before that the length, and these are all in feet, right? These, all our units here are in feet. Now, I told you that the length of our stake was 1, so what should be the magnitude of the unit vector? Or, sorry, what's the magnitude of the unit vector is 1, right? But what's the magnitude of the position vector if my stake has a length of 1? It should also, actually, so my position vector and the unit vector are the same because my position vector has a length equal to 1. And so this is just going to be a minus not a minus 2 point, how about a minus 0.2i, a positive 0.3j, and a minus 0.93 k hat. So there's our unit vector because the magnitude down here is equal to 1.0. Okay, but if it wasn't, you could do the same process. Okay, so now we have the unit vector. Now we can do the dot product. So FAB onto AC, and this is going to be kind of a long line here. Let's see, AB we have, we can do this. Why don't we do this in the component bracket form here? So we have a 74, we have a 112, and a 148. There's our force vector. And then we're going to dot this with a minus 0.2, a 0.3, and a minus 0.93. And so then this is going to be equal to 74 times minus 0.2 plus 112 times a 0.3 plus 148 times a minus 0.93. And so this becomes a scalar, right? It's no longer, those are no longer ij's and k's. This becomes a scalar, and I get here, actually when I do the math, I'm going to get negative 118.84 pounds. So negative 118. What does that negative mean? Why do we get, we should get a scalar, but we have a sign on this. Actually, the dot product gives us a little bit of information about the direction that things are going. This tells us, that means right there, that the projection goes opposite the unit vector. That unit vector that we picked from A to C, because which way is that stake going to go? If it comes, I talked about it, it's going to come flying out of the board, right, and hit me in the head. But which way did our unit vector go? Our unit vector went into the board. And so it's telling us, no, it's not, it's telling us the force is not going to go into the board. The force is going to come out of the board. So it's really cool, actually, that it gives us that additional information. And then the 118, that's telling us that there's actually, out of that 200 pounds, there's 118 pounds that's going directly along this stake here, and it's trying to pull this stake out of the board. And so now we know exactly how much is trying to pull us out of the board right there. There's 118 pounds trying to pull this out of the board. So that's the projection of that 200-pound force, or that force vector, A to B, onto that line from A to C. Now, how about for the parallel? We just did the parallel. How about the perpendicular? Remember, the perpendicular component, if we're still in part A, And so the perpendicular component, we want to find the scalar. And so this is part A is the scalar. Still, we'll do the vector in a second. So part A with the scalar, we go back, and the idea is that we have a 200 pound to start with. So 200 squared has to be equal to 118.84 squared plus the part of AB that is perpendicular to AC. So FAB perpendicular to AC squared. And so we can solve FAB perpendicular to AC is just the square root of 200 squared minus 118.84 squared. And I find it's equal to 160.86 pounds. And maybe I use that to say, well, is it going to like break through the board, right? Is it going to like shear the board off of the wall or something like that? That tells me how much is perpendicular to the stake. And it doesn't tell us necessarily what direction it's going in. It just tells us that it's acting perpendicular. We don't know if it's perpendicular like here, if it's perpendicular here, right? We just know that it's perpendicular to the stake. Okay, moving on here to part B then. And for part B, we want to find, this is the scalar stuff, or sorry, this is the vector stuff. And so we can find our force vector of the parallel component of FAB onto AC is going to be the minus 118.84. So actually, we keep the sign. When we do our vector operations, we're going to keep that sign. Keep any sign that we get out of there for our vector operations. You see, I dropped the sign when I did this stuff up here for this part, right? It was squared anyway, so it doesn't really matter. But we keep the sign for vector operations because what's going to happen is that sign is actually going to take care of itself. So the vector operations will do all the work for us. And so what do I need to multiply that by? And let me ask somebody else here. How about Kaylee LaRue?
What do you have to multiply it by? Is that what you're asking?
Yeah. How do I have a magnitude essentially. How do I get a magnitude into a vector?
Multiply it by the unit vector.
Yeah, absolutely. The same unit vector that we used before, and the unit vector from A to C. So this is kind of interesting because look at this equation and then look at this equation. Don't they almost look exactly the same? Right? It's like we have, but this one up here, the first one, that's a vector dotted with a vector. This is a scalar times a vector, but it's like, it's still, we're using the unit vector twice, aren't we? Okay, so now if we do the math here, we're going to find AB onto AC. I take my minus 118.84 and I'm going to multiply it times the unit vector, which we know is a minus 0.2, a 0.3, and a minus 0.93. Look what happens when I keep this sign right here, right? We're keeping that. Look what happens. I take a minus 118 times a minus 0.2. So actually I end up with my x component being a positive. And I get a positive 23.77i. And then I take my minus 118, I multiply it by a positive 0.3. And so I'm going to get a negative in the j direction, minus 35.65j. And then I have a minus times a minus for the last one. And so I'm going to end up with a positive 110.52 k hat. And we can see it in all of these components, but let's focus on the k component. We know that stake is going to come out of the board, right, and hit me in the head, which is going in which direction relative to our coordinate system? It's going in the positive k direction, right? It's going in the positive z direction. It's coming out of the board, so it's coming in the positive z. Look at when we kept that sign, we end up with a positive z. And so we can see the vector operations, keeping that sign for vector operations, it flips everything for us and makes sure that in the end it goes in the correct direction. Okay, and then our last one here is we can find the vector that's perpendicular to AC, and that is simply going to be taking our original force vector and subtracting that force vector that we just found, the AB, onto AC. And so that, let's see, our original vector was 74I plus a 112J plus a 148K. And then I'm going to subtract off the one that we just found, which is a 23.77I minus 35.65J and a positive 110.52 K hat. Subtract that off, and I'm going to end up finding here, I get 50.23 in the I direction. I get a 147.65 in the J direction, and I get a 37.48 in the K direction there. And then, no, this is not the force it can resist. I see a question in the chat there from Kalev. This is the force that's applied to it. We really haven't talked about the force that it can resist. In there, we're really just finding how much of that 200 pounds is projected parallel and perpendicular to that original stake there. So that takes us through everything that we really need to be able to do. It covers all of our learning objectives there. This is, you know, we're doing it for statics. Actually, I did the same thing for a project a bunch of years ago to figure out how much input energy you get into a solar panel based on the angle, the location of the sun and the angle of the solar panel. And so what I did is actually I used the dot product to figure out the projection onto that, and then I did all the other stuff that we did to find the perpendicular, because it's actually the perpendicular component of the sun that tells you how much input energy you're getting into that solar panel. So not just statics, lots of uses for this, for the dot product and all these vector operations stuff. You all have a great Friday. Have a great weekend. We'll see you on Monday. Remember, recitation's on Sunday.